So there's a specific equation that helps me to relate the wavelength that I have to that energy difference in the higher excited energy state to whatever lower one it goes to, either a lower excited state or the ground state. So that equation is called the Rydberg equation. So the Rydberg equation is going to relate my energy levels, my N values, to my wavelength. So here, this is 1 over wavelength, and then this is my Rydberg constant, and then I have my N equals 1 and my N equals 2 of my energy levels, okay? Now, N equals 1, 2, and all that, you might be like, okay, well, I don't know which one it is. And so this is able for us to kind of predict what that energy level should look like. So if I know I went from an N equals 3 to N equals 2, what it is. Now, we can solve the Rydberg equation one of two ways. We can either use the Rydberg equation constant and plug it in here, or we could actually use this guy. This guy is going to take into account the energy that was associated with this wavelength. And so here it's still 1 over wavelength, and here I still got my N's. I'm being a little more specific. Instead of 1, I'm saying what's the final, what's the one I'm going to, and what's the initial. So if I initially was at a 3, and then I went to a 2. And here, this would be my adjusted Rydberg constant and related to my HC. Because remember we said that we know the energy is related to the wavelength with that combined equation. So this is the equation that we're going to use more often. But you might see people use this one, like say in lab or whatever. Both work, just depends on what you start with, what you're given, and what you're looking for. All right, so let's do a practice problem. So this says, calculate the wavelength in nanometers of the photon emitted when an electron transitions from the N equals 4 state to the N equals 2 state in a hydrogen atom. So lots of words. So what am I looking for in the problem? I'm looking for the wavelength. So I'm looking for the wavelength, and I want it in nanometers. Okay? The next question is, well, what did they give me? So they gave me the N equals 4 state and an N equals 2 state. So where did I start? What would be my initial N value? Where does my electron start? So my electron goes from the N equals 4 to the N equals 2. And we know it's emission. So it's got to be higher to lower. So my initial N is 4 and my final N is 2. All right, so I've got N's and I need wavelength. There's only one equation you're going to learn this whole semester that has N's and wavelength, and that's my Rydberg equation. So you want to go and then you want to use this guy, okay? So now we take our Rydberg equation and we're going to plug everything in. So our Rydberg equation was 1 over lambda is equal to 2.18 times 10 to the negative 18 joules over HC, 1 over NF squared minus 1 over NI squared. So let's start plugging stuff in. 1 over lambda is equal to 2.18 times 10 to the negative 18 joules, and that's all over H. So what was H? So H was Planck's constant. Let's go all the way back. Here we go. It's the same H that's in this equation, because that's what we're getting. We're including the energy, and that's where we get the HC in that Rydberg equation. So H is Planck's constant. So it's just a constant. And remember, C is my speed of light. So both of those are just constants. Keep going. Okay? So H is my Planck's constant, 6.63 times 10 to the negative 34 joules times a second. Speed of light was 3 times 10 to the 8th meters per second. That whole thing is times 1 over NF. And F was the 2 squared, minus 1 over 4 squared. All right, so we got a lot of math. So I recommend you kind of going slow and slowly working through this problem. So 1 over lambda is equal to, now at this point, what you could do is you could say this divided by this times this, okay? So start here and then divide it by this guy. So kind of do this whole math. If you need to, you could do this times this and then do top by bottom. But I'm just going to do this whole math. I'm going to do this guy divided by this guy. And that's going to give me 1.09603 times 10 to the 7th. Now we need to figure out what my units are. I have a joule up top, and I have a joule on the bottom, so they cancel. I have a second here, and then I have a 1 over a second here. So second is on the top, on the bottom. So seconds, 1 over a second, so they cancel. So the only thing left I have is a meter, but it's a meter in the bottom of my math here. So what happens is I need the meter to be at the bottom, so it's a 1 over a meter. Now let's work out this side. So 2 squared is 4, and 4 squared is 16. All right, let's keep going. One over lambda is equal to 1.09603 times 10 to the 7th, 1 over a meter. And then 1/4 minus 1/16 is 0.1875. Okay. Then you want to do the multiplication here. Start multiplying those two together. And you get 2.05506 times 10 to the 6th, 1 over a meter. Because this doesn't have any units, because it was just the ends. 1 over n squared, 1 over n squared, so no units. All right, but we're not done. This is 1 over a lambda. I wanted lambda, not 1 over a lambda. So what we have to do is we have to change. There's a couple ways you could think about this. You could first think about it like, okay, if I multiply this over, so then lambda would be over here, then I would have to divide this over. Okay, that's one way for you to think about it, is move the lambda over and then divide that over. So you'd have 1 divided by 2.05506 times 10 to the 6th, 1 over a meter, is equal to lambda. Another way you can think about this is if I want lambda on top, if I flip these so that it's lambda over 1, then I have to flip this. If this is 2 over 1, then I have to flip it so it's 1 over. However you want to think about it. So flip it, get that. So now you want to do 1 divided by this guy. If you do 1 divided by that guy, you get 487 times 10 to the negative 9 meters. And the reason we get meters is because this is 1 over a meter, but he's on the bottom. So if he's a 1 over a meter when he's on the bottom, it actually flips him to be a meter. Okay? Now you might say, okay, cool. I finally got my lambda, my wavelength. I'm done. But what did we want it in? We wanted it in nanometers. So I got one more step. So I have meters. I want nanometers. So if meters are here, I'm going to put them on the bottom to cancel, and nanometers go on top. Nano is 10 to the negative 9. If the n's on top, the 10 has to go on the other side. So my meters cancel, and I get that my lambda is 487 nanometers, which is in my visible light spectrum. Okay? So that's my Rydberg equation. And this is the hardest equation for this chapter. Okay? So the biggest thing that people try to do is they try to do all the math in their calculator at one big fatal sweep. You don't want to do that. If you try to do all the math in one big fatal swoop, you're going to get something wrong. So take your time and go step by step working it out. Okay? And remember, we know what my visible light spectrum is. We know it's 400-ish to 700-ish nanometers. So my number wasn't in that, and then that kind of gives me an idea. Unless it doesn't say that it's visible light. Now, here it doesn't say it's visible light, but we're talking about the hydrogen atom. And the hydrogen atom, all of its transitions are in the visible light. All right? So you want to kind of practice this because this is the tricky math for this chapter if people kind of get confused. All right? So now the next thing we're going to talk about is now that we kind of know what's happening with my electron, and we know where my electron's located at this point, Now we kind of want to know a little bit more details about the electron itself.